Welcome, Math 30-2s. We're going to look at exponential logarithmic functions today. So today we're going to start a review of the exponent laws. So something you already know, just have a quick look at it. Have a quick notice that this whole thing is called a power. Exponent is n, the base is x, but the whole thing is called a power. All right. Complete the following exponent laws. The product law. X to the m times x to the n. Rule says keep our base and add the exponents. Quotient law. We're dividing powers of the same base. Keep our base and subtract the exponents. Power raised to a power. Keep our base and multiply the exponents. Power product means everything inside the bracket gets the exponent m. And same thing with a power of a quotient. Everything inside that bracket gets that exponent. Note the restriction. We can never have a denominator 0 because we cannot divide by 0. Our integral exponent rule says x to the negative m is the same as 1 over x to the positive m. And again, we can't have a denominator 0. Division by 0 is undefined. Also, we've got the rational exponent law. The x to the exponent mn means the nth root of x to the exponent m. Or sometimes you're going to see it written as the nth root of x all to the exponent m. Both those are acceptable. All right. Let's add the zero exponent law. Which states that any base to the exponent 0 is going to equal 1. And let's also talk about in advance of the integral exponent rule. Let's say I've got a fractional base, something like x over y to the exponent negative m. X over y to the exponent negative m. When you've got a fractional base to a negative exponent, you take the reciprocal of the base and make that exponent positive. All right? Great, so let's use these rules and simplify the following. X squared times x cubed, keep our base and add the exponents. 2 plus 3 is 5. X6 divided by x squared, keep our base and subtract the exponent. 6 minus 2 is 4. C, keep our base, power raised to an exponent, we keep our base and multiply. 5 times 4, which is 20. For D, everything inside the bracket gets the exponent, so it's going to be x cubed over y cubed. For E, same thing, everything inside the bracket gets the exponent, so that's going to be 3 cubed and x cubed. And now we can simplify that because 3 cubed is 27. So that's the best way to write this, 27x cubed. Looking at example 2, write each expression without brackets and with positive exponents. So x to the negative 3, by our law, says that's 1 over x to the positive 3. Negative exponents become positive in the denominator. And that's as far as we need to go. For part B, get rid of the brackets. So 4 times 2 is 8. And we're multiplying powers of the same base, so we add 3 plus negative 4, which is x to the negative 1. Now notice I've got a negative exponent on the variable x, not a negative exponent on the 8. So the 8 stays in the numerator. X to the negative 1 becomes x to the positive 1 in our denominator. Well, you don't need to have the exponent 1 there if you don't want to, but it can be written there, but it's usually just written as 8 over x. Part C. Power of a product, or power of a product rule. We've got 2x to the 4th all cubed, so that means the 2 is going to get cubed, and the x to the 4th is going to get cubed. So they're both going to get cubed. 2 cubed we know is 8. X to the 4th, that rule says keep our base and multiply the exponents. Part D, the 5 is not affected by the exponents, so we're going to keep that outside the brackets. The 3 is going to get cubed, so 3 cubed is 27, just like example C. And the x squared gets cubed, so you keep the base and multiply those exponents. And then the last step, we're going to multiply 27 and 5. All right, so 27 times 5 would be what? 135 x to the 6th. Looking at example E, our rule says keep the base and subtract the exponents when we're dividing powers of the same base. So the 5 is unaffected. we keep our base of x and subtract -3 minus -2. So we're really doing integer work. Keep our base, so -3 subtract -2 is -1. Well, that's the exact same as the question right above us in part B. So 5 does not have a negative exponent, but x does have a negative exponent, so x becomes a positive exponent in the denominator. And looking at f, we can go 12 divided by 3 is 4. B -1/2 divided by b, we keep our base of b and subtract the exponents. -1/2 minus 1. So if I'm going to subtract -1/2 and -1, we could rewrite -1 as an equivalent fraction as -2/2. So I've got 4b to the -3/2. And now I want to write this with a positive exponent. So 4 does not have a negative exponent. That stays in the numerator. B to the -3/2 becomes b to the +3/2 in our denominator. And that's all they wanted. Write it with a positive exponent. If you want to, we could rewrite this as 4 over the square root of b cubed. But that's not necessary. It just asks us to write this with positive exponents. All right, let's look at example 3 on the next page. Without using a calculator, wants us to determine. So example 3, without using a calculator, determine the exact value of the following. You can verify with the calculator if you'd like. So 2 to the -3. 2 to the -3 is like saying 1 over 2 to the +3. And evaluate that. That's 1 over 2 times 2 times 2. 9 to the 3/2 means the square root of 9 all cubed. Square root of 9 is 3. And that's still going to be cubed. 3 cubed is 27. 25 to the exponent 0 is 1. 16 to the -1/2. Step 1, make our negative exponent positive. So that becomes 16 to the +1/2. And then exponent 1/2 means square root. So square root of 16. So 1 over 4. And so we can verify these with the calculator. So let's have a look at that. So 2 to the exponent -3. 2 to the exponent -3. If you just press enter, you're going to get a decimal value. So if you go math fraction, oh, that's not so good. Delete 2 to the exponent -3 as a fraction will give us 1/8. So we've seen that that is correct. All right. Let's try 9 to the 3/2. 9 to the exponent 3 divided by 2. So that'll give us 27. And 25 to the exponent 0, well, we should know that's 1, but we can check it on the calculator. And finally, 16 to the exponent -1/2. Again, if I just press enter here, I'm going to get a decimal value. If I go math fraction, it'll give us the answer we had in our workbook as 1/4. Great. So you guys can try questions 1 through 3. Then you come back here and we'll look at the rest of the notes. Investigating the inverse of a relation or a function. Part 1. All right, so let's investigate the inverse of a relation or a function. Part 1. A function or relation maps each element of set A, which is a domain, to the elements of set B, which is the range. So the diagram shows the function is a half of with the domain 1, 2, 3, 4 and the range of 2, 4, 6, 8. So here it says A is a half of B. 1's a half of 2, 2's a half of 4, and so on. Complete the following. The graph of the function consists of the points 1, 2, 2, 4, 3, 6, and the last ordered pair would be 4, 8. The inverse of a function or relation undoes what the function or relation does. In other words, the elements in set B are mapped back to the elements in set A. So the inverse of the function is half of would be the function is double of. So the domain becomes 2, 4, 6, 8, and the range becomes 1, 2, 3, 4. So B is the double of A. 2 is the double of 1, 4 is the double of 2, and so on. So complete the following. The graph of the inverse of the function consists of the points Ordered pairs now are 2, 1, 4, 2, 6, 3, and 8, 4. Part C, plot the points representing the function on the grid. So let's go to our original function and plot those points. 1, 2, 2, 4, 3, 6, and 4, 8. So x was 1, y was 2, 2 and 4, 3 and 6, 4 and 8. That's part A, plot the points representing the function on the grid. Part B, plot the points representing the inverse of the function on the grid. All right, so we'll use a different color, and I'll plot the inverse as green. So those points when x is 2, y is 1, 4 and 2, 6 and 3, 8 and 4. So we'll plot those points on there. And then it asks us to join the points together to show the function and the inverse of the function defined for the set of real numbers. All right, so there's my inverse function. It's going to go through the grid, arrow both directions. Here is my original function, all the way through the grid, arrow in both directions. Now it asks you to draw a mirror line which represents the axis of symmetry of these graphs. So I'll make my mirror line in red. Note that on a mirror line, things will be reflected. The only things that won't be reflected are the things that lie right on the mirror line. So that's the point 0, 0. That lies right on the mirror line. That point didn't change. So my mirror line should be halfway between these two lines. So that'd be the mirror line. All right. Someone call it the axis of symmetry, but that's fine. Let's look at the next page. Consider the table shown for the original function and its inverse. Notice that the x and y coordinates in the function have been interchanged to get the x and y coordinates in the inverse. All right. So my original function has the points 1, 2, 2, 4. The new function is 2, 1, 4, 2. So those points have been interchanged. The equation for the function is y equals 2x. That's our original function. How do I find the equation for the inverse function? Well, let's have a look. The inverse function equation, it tells us to do the following steps. Interchange x and y to get the equation of the inverse. So y equals 2x. Now x should equal 2y. All right. And now write the equation of the inverse in the form y equals. All right. So in the form y equals, I want to solve for y, so I can divide both sides by 2. So x over 2 will equal y. Or you might want to say it as y equals 1/2 of x. So there's the equation of our inverse. Note, if I'm going to interchange the x and y coordinates, the y here becomes the x there, the x here becomes the y there. The same thing is going to happen to our domain and range. Domain from the original function becomes the range of the inverse. Range of the original function becomes the domain of the inverse. Let's look at part 2. The first diagram shows relation is the square root of, on the domain, -3, -2, +2, +3. My goodness. So A is the square root of B. -2 is the square root of 4. +2 is the square root of 4. And so on. Complete the second diagram to show the inverse of the relation is the square of. So we're going to say B is the square of A. So 4 is the square of -2 and +2. 9 is the square of -3 and +3. So the inverse interchanges the x and y coordinates and undoes the original function. So let's complete the chart. For the original function, the relation in words is the square root of. The coordinates of the points on the graph would be -2 and 4, +2 and 4, -3 and 9, +3 and 9. The equation for this function would then be y equals x squared. The domain, well, x is simply plus and minus 2 and plus and minus 3. The range is simply 4 and 9. For our inverse function, we were told that that is, in words, is the square of. And those ordered pairs would be 4, negative 2, 4, positive 2, 9, negative 3, and 9, positive 3. And the equation for this should be x equals y squared. Or if you want to solve this for y, you take the square root of both sides. And the rule when you take the square root of both sides is to include the positive and negative. So x equals y squared, or y equals plus or minus root x. Domain would be the range from the original function. So the domain of the inverse would be 4 and 9. And the range of the inverse would be the domain of the original function, plus and minus 2, plus and minus 3. Beautiful. Next page. Plot the points representing the element. All right, so let's plot the points representing the relation on the grid. So the original function had the points negative 2, 4, positive 2, 4. So when x was negative 2, y was 4. When x was positive 2, y was 4. When x was negative 3, y was 9. When x was positive 3, y was 9. So there's our original function, and let's plot the inverse of the relation. So we were told the inverse points were when x was 4, y was negative 2 and positive 2. When x was 9, y was negative 3 and positive 3. There's our inverse ones. Part 3 says join the points together and extend the curves to show the relation and the inverse of the relation defined on the set of real numbers. So if I extend the curves, it's going to start at 0, 0, both these. I'm going to go forever. The inverse goes forever to the right, and the original function goes forever up. All right. Ask you to draw a mirror line which represents the axis symmetry of this graph. So our mirror line, again, the only point that doesn't change in this graph is 0, 0, and our mirror line would show up right here. All right, so there's our axis of symmetry. And it asks, what is the equation of the axis of symmetry? Well, a couple neat things about the axis of symmetry. We said earlier that the points on the mirror line will never change. And one point we know that never changes is the origin. That's been consistent the last two graphs. The coordinates of that point are 0, 0. What happens if I interchange those x and y coordinates? If I interchange them, I get 0, 0. If I pick another point on the mirror line, let's say this point right here, that looks like a point on the mirror line. That's the point 5, 5. X is 5, y is 5. If I interchange those 2 points, interchange the x and y coordinates, I get 5, 5. So points on the mirror line do not change. So what's that telling us about the x and y coordinates? They're going to remain the same. So the equation for this line should be y equals x. Those points are all the points on that line will never change if you take the inverse of them. So that would be the mirror or the axis of symmetry for inverse functions. Let's look at part 6. Complete the table showing the domain. All right, so let's complete this table. The domain for y equals x squared. The blue graph. We'll notice that the graph goes right forever and left forever. So our domain is x is any real number. And the range for our blue graph. This graph goes forever up, but nothing down. So y should be greater than or equal to 0. Our inverse function. The domain, x goes right or positive, but never left, so x should be greater than or equal to 0. And it goes forever down and forever up, so y is any real number. So continuing the idea with inverses, the domain of the original function becomes the range of the inverse. Range of the original function becomes the domain of the inverse. Okay, determine the inverse of a relation or a function. If a function relation is defined by a set of ordered pairs, the inverse is defined by interchanging the x coordinates and the y coordinates. If a function relation is defined by an equation, the inverse can be determined by using the following procedure. Interchange the x and y coordinates and then solve for y. If function relation is defined graphically, the inverse can be determined by a reflection in the line y equals x. Note the domain of the inverse is the range of the original function, and the range of the inverse is the domain of the original function. Let's complete example 4. Determine the inverse of the function defined by the equation y equals 5x minus 6. So step 1 tells us to interchange the x, y coordinates. So x equals 5y minus 6. And now it tells us to solve for y. So I'm going to add 6 to both sides. And I am going to divide both sides by 5. So y should equal x plus 6 all divided by 5. And that's the equation of the inverse function. All right, you guys have your assignment? Away you go.